I want to go through a few more example problems of playing around with our samples and how we calculate likelihoods of samples falling within certain parameters. So pretty much where we are right now, we're always going to know the mean and the standard deviation of the population. Right, so we may know the mean is 7 and the standard deviation, let's call it 2. And where we are here in chapter 8, we kind of need to know those. As we progress forward, we'll deal with what happens when we don't know these. But for now, we'll know the mean and the standard deviation of the population. And beyond that, we don't actually need to know, if the population comes from a normal distribution or a uniform or some funky looking distribution. At this point, it's not important to us in some sense. Obviously, that would be interesting in and of itself, but for the purposes of understanding our sample results, all we need is the mean and the standard deviation. Because as we take a sample from that, we know that the sample is going to, or the sample means are going to produce a normal distribution. Right, so let's say we take a sample, n equals 10, and let's say we do that, all as many times as we can. We know that that's going to produce, from the central limit theorem, we know that that gives us a normal distribution. Now, what we've been working on is how do we apply our z-score, z-value techniques to this sample distribution or distribution of the sample means, right? So each of these n's of 10, each of these samples will produce a sample mean, and that sample mean follows a normal distribution. So the process for that, again, we can do much of what we've done, in chapters 7 and perhaps even earlier, as to how to calculate certain areas within or underneath the curve, right? So we can pick any type of window that we would like, and we can calculate the area within. Now, what that requires is that we know, again, the distribution mean and standard deviation, right? And so we've indicated that as the x bars. So the mean of the x bars and the sigma of the x bars, or the of the distribution here. So and again, as we've shown, we don't need that x there. We have these two simple equations that give us our distribution values if we know the population values. Okay, and so in our case here, what did we say? 7. And this is going to be 2 over the square root of 10. Okay, and I think that's, what is the square root of 10? It's 3.16. So 2 over 3.16. Maybe we can get a little cleaner of a value that we can plug in. We'll call it for our purposes here 0.63. If it's, we'll use that for rounding purposes. So we now know the mean and the standard deviation of this of the sample distribution. And so all that's left to do to calculate ranges here is to follow the same path we did earlier when we dealt with the population. And that revolves around the z-score. Right? And so when we were interested in if we had a normal population, we use the x minus mu over sigma, and we're going to do the same thing here, only adjusting that for to make note of the fact that we're dealing in the sampling distribution, or the distribution of sample means. Okay, but then the process remains the same. We're gonna depending on what we're looking for. So again, if we are interested in the probability of falling between, let's call this maybe we're interested in 5 to 8. So what's the chance that this distribution, that a sample drawn falls somewhere between 5 and 8? In that realm, what we're looking for, right? We don't know. What we're really interested in is what percent chance or what likelihood is it to fall in between there. We know the percentage in the z-score. These are highly related, right? We find it just by looking at the table. So we don't really know the z-score. But what we do know is we know the x bar that we're interested in, right? So in this case, we're going to have to do it twice, but we know the x bar. We know the distribution mean and sigma. So we know these values. And so we're going to use these three, plug them into this formula, and it'll produce a z-score, right? So if we know we have 4 variables here, we know 3 of them, it's going to give us the 4th. Okay, so let's walk through that. I'm just going to switch colors here a bit. Okay, so let's start with 5. So what is the z-score of 5? Well, 5 minus 7 over, we'll call this 0.63, is going to give us -2 over 0.63. And let's just let Google tell us what that is. And we get -3.17. Okay, so again, I haven't drawn this very well to scale, but we get a z-score of beyond -3.1. So when we pull up our z table, because again, all we found thus far is the z, and what we're really interested in is what's the chance of falling outside of 5. Right, let me redraw this and maybe put 5 in a better context. 5 actually ends up being way over here. Okay, so we're interested in what's the likelihood of falling outside. Wait, did I say inside? I said between. Always good to verify. Okay, so we're interested in the area between 5 and 7 in this case, right? The mean and 5, and we'll add on that extra part on the other side of the mean. Okay, so from 3.17, a z-score, let's pull up the z table. And again, you probably are getting familiar with this in that the z table ends out here at 3.09. And so we could again crunch the exact value, either plugging it into Excel or finding an online system that would do it. But for our purposes, we can let's use 0.499. Okay, we could probably even just write it down as 50%, but let's call it 0.499. And so from that, we need to add the other part, right? So we have one other half here. We are interested in, that color is not going to work. We are interested in the value between 7 and 8, right? Or between the mean and 8. That's supposed to be an 8 there. And so to do that, we need to just redo the process. Z is equal to 8 minus 7 over 0.63, which is going to be, that is a 1.5, we'll call it 1.59 with a little rounding. Okay, so 1.59 standard deviations above the mean. And so when we go and look that up on our z table, 1.59, we can scroll over. Just remember, so this is the 0.09 on the far end. So when we get to 1.59, we see 0.4441. Okay, so when we take this back, we want to then add these together, right? So we're interested in both halves here. So our final answer is going to need to include both. So 0.4441 plus 0.499, we called it 4990. We could probably, it's probably more than that slightly, but we'll go with that. And just to finish it off, what does that give us? 499 plus 0.4441, and we get 0.9431. Okay, so we have a 94% chance that this sample would fall between 5 and 8. Okay, and so clearly I did not write or draw that one to scale, and probably not even the one on the right. So we're quite sure that we'll find a sample between 5 and 8, which is about 95%, or we're getting close. What if we wanted to find exactly the range that would include 95% of samples? Okay, so this is a slightly different question, but let's take a minute or two and we can crunch that out. So what this relies upon, again, what I'm interested in now is what values are going to give me where 95% of the samples fall within. Okay, so in this case, I know the percentage, right? I know the percent, and I don't know the X bars. Okay, so the process is going to change a little bit. I'm going to just flip over to a new screen. But let's stick with so we know the we still know our means here, and they are still 7, and we know the let's just write this down to remind ourselves. Still dealing with the sample size of 10, and what did we call that? 3.16, I think. That's not true. That was the top. What were we using? 0.63. That's all hidden. There you go. Okay, so just to remind ourselves, we have a mean of 7 and a standard deviation of 0.63, and we're interested in what percentage, we're interested in 95% falling between what two values, and we're going to consider this symmetrical. So when we think about this distribution, there's some value for which 95% is within the standard deviations, okay, stretching both directions. And again, this one won't come as much as a surprise, because at least we should be able to expect roughly what this is, right? So what does our empirical rule tell us? Our empirical rule tells us within 2 standard deviations. Now, this is not precise. The empirical rule is not precise. And so we're going to actually calculate the exact value. So to get us started, if we want 95% to fall within this range, what we really want, if we're gonna use our z-table, is we're gonna have 2 areas, each of which is not 95 but half of 95, so 47.5%. Right, so each of these will contain 45 or 47.5%, and so between the two, they'll be 95%. So that is the percentage. Now remember, so we are going to want to deal with the z-score. We need x bar minus mu of x bar over sigma x bar. So what we are really after, again, is this x bar. What is this cutoff value, is one way to think about it. Where is the cutoff in this distribution of which 95% is going to be within this range? So we know the percentage, and remember the percent is related to the z-score, right? We can quickly convert between the two using our z-table. So we know we want 47.5%. So let's go back to our z-table. And what are we looking for? Again, this time we're reversing the direction, right? So in the previous example, we were looking up a z-score, 0.332 or something, and then looking up what percent that's related to. This time we want to start with the percent. So we're starting in the table. We're looking for 47.5% or 0.475, and then we'll see what value that's associated with. So we can find it if we hunt and pick for it here. We get 0.475. That's associated with 1.9 and then 1.96. Okay, so 1.96 gives us, or that's the z-score that is related to 47.5%. So 1.96. Okay, and that's the precision. So the empirical rule tells us 2. The actual exact value here is 1.96. So we can use that. So 1.96 is equal to, we still don't know x bar, but we do know these other values. Right? We know this is 7 and we know 0.63. And so now we have what we need to solve for x bar. And so just some simple algebra here. 1.96 times 0.63 is going to give us so let's just rewrite this. This is 1.23 roughly equals x bar minus 7. And so what does that give us? That means we're going to be at 8.23. Okay, barring a little rounding, you might have gotten slightly different. But we find a value of 8.23. Okay, what does that actually mean? That value is, maybe I should have written it in yellow, but this is the cutoff that gives us 47.5% between the mean, which was 7, and that cutoff at 8.23. 47.5% of samples are going to fall in that window. So that's only one of the two cutoffs, right? We need to know the other direction. And in fact, this, because it's symmetrical and because we just want to go a certain distance in each direction, what we really are using is this 1.23. So if we go 1.23 in both directions, we'll then have 95% collected. Okay, so that becomes, what would that be? That would be 5.77. So if the window between 5.77 and 8.23 is going to give us 95%. Okay, and so sometimes you'll see it written this way, usually with some brackets around it. Another way to write this would be to say 7 plus or minus 1.23. And we'll kind of use both of these moving forward when we start to play around with what are called confidence intervals. But this is a way to express the range through which, or between which 95% of our samples would fall. So in this video, hopefully it's a little more practice and a little more example of seeing not only the finding the z-score and the certain percentage for known values, but also what if we don't know the values? What if we're interested more in the values from a given percentage? So again, we can be flexible with this z-score situation here, right? So we don't have to always start and stop in the same spots. As long as we can find a way to know 3 of the 4 variables, counting these as the 4 variables. Again, percentage and z-score are basically one and the same, just whatever you find on the table. As long as we know 3 of these 4 variables, we can always solve for the other variable. And so as we progress, a lot of times it's not going to be the same flow that we initially learned it as.